Good morning. It's great to be with you at ARPA-E this morning and to be able to talk with you on a topic I'm very passionate about. I'm very passionate about computing, and I'm very passionate about energy. And if there's one thing you take from the talk today, you'll see that there's, in fact, a very direct correlation. I want to thank Danny Cunningham and ARPA-E for inviting me here today. We've gotten a chance to know ARPA-E better through collaborations from AMD and ARPA-E over the last couple of years. And again, great pleasure to be with you here today. Let's jump in. Well, no surprise when you look at the couple of the trends that I'm going to show you as we get started here, because you all are probably using AI applications every day. If you're running ChatGPT, you're running Gemini, you're running Anthropic or Perplexity, you are in fact using these large language models. And the thing that I want to correlate that to you is the computation that's required to train these models is actually immense, and it correlates with the parameters in these models. So you hear about each one of these new models, and you hear a number associated with it. It's like, wow, I'm running Llama 3.1 70 billion parameter model versus I'm running Llama 3.1 405 billion parameter model. And of course, what you get with more parameters, you get more accuracy, you get more breadth and depth that generative AI model can assist you and can bring more productivity, and then you can fine tune upon that. So that trend for more and more parameters correlates with more and more compute capacity. And more compute capacity means more and more energy required to train the model. So it's an inexorable trend that we're on, and look, there's innovations that show us how we can be more efficient, and we'll get into that. Is the need for more energy sources and more efficient energy. And the reason is clear, because when you look at the trends that we're on, we've just come out in the last 2+ years with exascale computing. So that's supercomputing on the order of a quintillion flops, math operations per second. A quintillion, that's a 1 with 18 zeros behind it. And so that was a huge milestone, driven by the Department of Energy challenge that was put out there, and we'll get into that more in just a minute. And so think about all the work to get to this, what was thought unattainable milestone of an exascale. But innovation rules. We'll get the next 1,000 improvement. We'll hit a zettascale. But if we don't have innovation, both for new energy sources and energy efficiency, we're not going to have the power to be able to run. And the reason is, when you think about the gains that we're making in computing, we're doubling the computing capability of a CPU and separately a GPU about every 2 years, a little over every 2 years. But when you combine it at the system level, we're actually doubling it just over 1 year, 1.2 years, we're doubling that capacity. But the energy efficiency gains is about half that rate. So you're seeing compute capacity scaling at double the rate of the efficiency. We have to bend that curve. We have to drive more innovation to be able to fuel the computing that we need in our society. And so just a few things I want to just talk about that trend. So AI is becoming pervasive, and it's accelerating now as AI finds its way into every form, not only of our work and scientific pursuits, but our day-to-day lives in terms of driving up productivity. So a few points. One, I'll just highlight to you that when you're using a generative AI model that was trained on this massive computer, and when you're running inferencing on these huge models, you're using supercomputers that were once only available in national labs. Then it extended to be in these massive hyperscale installations. So supercomputing is now available to the masses. The other point I'll highlight is look at the discoveries which are they're coming out of this kind of computing. We've been working with drug discovery companies. We've been working with the NOAA on weather prediction accuracy, on the supercomputers that we've been partnering with are working on new drug discovery. You look at part of Oak Ridge National Lab, it's been opened up to just amazing breakthrough science. And so now, as AI becomes more pervasive, what are we seeing? What we're seeing is an insatiable demand for these kind of applications because it's such a huge productivity gain, because it accelerates our ability to innovate. And so AI adoption is going to do nothing but grow. We're going to continue to see more and more a convergence of the approaches driven by national labs such as the DOE has sponsored and we have here in the United States, and AI compute, because we need massive scale for these emerging large language models. But that leads to the conundrum that we have, and that is that insatiable demand for more computations. We find this myriad of applications is going to drive an equal insatiable demand for more power. So that leads me to, the journey that we've been on. How do we drive that incredibly steep and accelerated curve for computation while doing it in such a way that we innovate on both power sources and energy efficiency? And this is a call out I want to make to the Department of Energy and highlight, some of you may not know, the journey to how we got to those quintillion math operations per second of an exascale computer. It started years ago. I took the role of CTO at AMD back in fall of 2011, and we were bidding on a program in DOE called Fast Forward. It was one of what was to be 3 forward programs, putting out there a grand challenge to all of us in the industry of how we could innovate to crack that barrier of an exascale computing. And so we engaged at AMD. It was huge for us, that kind of public-private partnership. I will tell you, we wouldn't have put the engineers that we did on the problem, the number that we did, and to be able to take on this grand challenge without this program. This is what spurred us to make the investment, ourselves and other companies. So it was a bake-off over these forward programs. And then it led to the bid in 2018, and AMD, along with our partner Cray, HPE, were awarded the first, what would eventually be the first exascale computer, which is the Frontier system in Oak Ridge National Lab, which came online in 2022. It sort of came in just under the wire for the supercomputing conference and hit that mark of an exascale and was published at that time. So Frontier in 2022 was the world's fastest computer. It's an AMD CPU, it's an AMD GPU with HPE and Frontier scientists that collaborated to bring not just one exaflop, but as we came together in that collaboration of government, industry, and also academia. We brought universities with us. We continued to tune, and not only did we break an exaflop, but now peak is 1.7 exaflops. And it was superseded by the program El Capitan at Lawrence Livermore National Labs, which I had the honor of attending the dedication just in February of this year. And that is over 2 exaflops. So it's an excellent example of public and private partnership, and one that we certainly embrace at AMD. But the other thing we embrace, and why it is that we were drawn to that exascale program when the DOE put out that grand challenge, why were we drawn to that, is that's who we are at AMD. We love a challenge. And when you look at this challenge of compute being gated by the ability to have sufficient energy to match our insatiable growth that we drive with innovation and demand, to meet the demand, we set out an audacious goal back in early 2021. So 5 years ago, just almost 5 years ago. It was actually late 2020, as we first conjured up the goal. we said that we would have a 30x improvement in compute per watt of energy, so the energy efficiency of supercomputing by the end of 2025. And what we wanted to do was to beat that industry rate. Remember, I told you that the industry rate of energy efficiency gains was about a little over every 2 years, while the computation was doubling every year. So we wanted to beat that curve. And we knew that it wasn't just getting to a new semiconductor technology node, that it would take innovation more holistically across all of the design elements that you can bring to bear from a system standpoint, of the silicon all the way through the software stack and applications. And again, I point to the partnership with the 2 supercomputer programs, the 2 exascale programs that we have with Department of Energy, bringing together scalar compute of a CPU, the parallel and massive vector computation of a GPU, and AI acceleration of the multiply accumulates, the base underneath our machine learning algorithms. We combine that into a single chip. And so we synergize that CPU and GPU, that heterogeneous computing, and that was with the MI300A, which is powering the El Capitan system and now commercially available out in many compute centers. And that provided a huge boost. And then because we use chiplet technology, we were able to adapt that design very quickly to be an AI-optimized chip. So we just took out the CPU chiplets that we had embedded on this single heterogeneous device, and we made it all GPU, focused on maximum efficiency of AI computation. That's the MI300X, and you saw that we achieved a 24X. And I can tell you, here we are at the beginning of 2025, we're right on track. We have more innovations coming, so we will bend the curve, and we will achieve this 30x improvement in efficiency by the end of this year. And so, it's appropriate for this conference, to highlight our commitment. We're not alone. Our peers in the industry face the same dilemma. And so as you work with the semiconductor and the chip industry, know that we're committed to this innovation that's going to drive efficiency. What we've been focused on this for over a decade, and it took a mindset change. And I think it's important for this audience to understand, because you're going to be working with people that may need that mindset change, because energy is not often top of mind, certainly in our world. We're in a world of computation. And so if you look at the history of AMD, our culture was do whatever it takes. Get the maximum computation capability you can out of each and every single chip design. But what we saw a decade ago is we had to change. We had to change a mindset. We had to make energy an equal citizen. Performance is how we think about the trade-offs that we make every day. So that's both driving energy efficiency, it's energy delivery, it's the whole mechanisms of energy delivery. And now, as we've gotten into these massive AI data centers, we as a chip company have been brought into this new supplies of energy, new sources of energy as new data centers are built out. So it's a completely changing landscape. But it's not just the realm of supercomputers. It affects our entire portfolio. And we drive the same thing down to our embedded devices that need that efficiency. And of course, think about your laptop. You want all-day battery life, and that's what we've been able to achieve with these initiatives. So we're not done on innovation. This theme of this conference is innovation. And I've had the honor of being in this industry over 4 decades. And if there's one truism I've learned is don't ever count out innovation. I can't tell you how many times I've heard, well, we're doing great, but there's a fundamental roadblock, or the physics says that we can't get beyond, this next barrier. But we've always found a way to innovate. That next 1,000x at computing, that zettascale computer, zettaflop achievement, will take us leaning in even more on the kind of techniques I talked to you about with the frontier and the El Kappa 10 supercomputers. We're going to have to lean in, of course, continually on new fab technology. And now we're bringing those fabs to the U.S. to ensure that we have assured continuity of supply. But as I said, it's a holistic approach that's required. So we continue to innovate new architectures. We've been a leader in chiplet designs to be able to really increase the density of computation and the heterogeneity of that computation. About half of the energy is actually the interconnect of these devices. And so as we've gotten silicon to silicon chiplet technology talking to one another, where you're not going off a chip and burning tremendous energy to talk to an adjacent chip, that's brought tremendous efficiency. And we've been focused on photonics. And you're going to start, of course, we have photonic and optical interconnect at networking of scale out of the massive computers. But you're seeing that photonics interconnect coming and giving us a much more efficiency going forward. And then, of course, algorithms. Again, it takes a holistic design. And so we work very closely with the national labs here with DOE and across the world, and also the huge hyperscalers, Microsoft and OpenAI and Oracle and Google and the like, to really optimize the algorithms and the system level, the rack level optimization to achieve efficiencies we need. And when we do all of that, what we're going to take is the current path we're on, which I showed you this vision of a nuclear reactor required to run a zettaflop computer. We're going to bring that back down into the megawatts if we can continue to drive that kind of innovation that outpaces our historical curve. That is exactly what we're going to need. So that's what we are focused on at AMD. We're about exaflops all the way down to laptops. And it's really the point that I have the opportunity to highlight to you is that across that entire portfolio of a Fortune 100 company like AMD, energy has risen to the top. Energy is a first order optimization, as well as a focus in terms of source of energy and new types of storage, new battery technology, new interconnect technology. It's very far reaching in terms of what it drives us in terms of our investments, our research, and our development activities is to span that entire range of our portfolio. Very simply, again, I told you at the beginning I was going to leave you with one key point, and that is, for us at AMD and for the industry, energy is performance. It is that ability to give you the computation that you need, that you are demanding. So I really want to wrap up with really a thank you and a plea. A thank you. Many of you are in the Department of Energy. So again, I want to highlight to you the tremendous effort and partnership that we had with DOE, with industry partners, and with academia on achieving that grand challenge of exascale computation. But what I also leave you with is we're not slowing down. We're going to continue applying that across our portfolio. And here comes the plea that I leave you with. We're about partnerships. Because when you think about, when I say open, what I mean is the ability to interoperate, that there's not just one solution that locks you in. We are strongly supportive, and we do this with our AI software stack. We do it with all of our interconnect standards we run with. There needs to be a strong and vibrant ecosystem, and that's what will fuel that innovation of both computation and efficiency, is us having that ability to be open, to be able to partner on the standards and the ways in which we work together, and to get many different types of heterogeneous solutions, new accelerators. Think about quantum, which is coming. Quantum's an accelerator. So what you're going to see is the kind of heterogeneous computing we have today working side by side with quantum computers. You're going to take the kind of problems that can run on quantum, you're going to put them off to that quantum accelerator. But it's going to take deep collaboration. That's our commitment to you. That's my plea to you, is to drive that cry for collaboration across the industry. And with that, we've got such an exciting future. Those of us working on industry will not let you down. We'll keep on that accelerated path to give you the computation which you are demanding. Thank you very much.